I've always wanted to go to Mars. Haven't you, Bruno? Well, at least your sister rover, Rosalind Franklin's going to get a chance. She's going to launch to the red planet and look for signs of life. Now, in the last lecture, we were looking at the Earth-Moon system and finding out what it means to be a habitable planet. But now we're going to go further afield, out into the solar system. But what are the chances of finding life out there, and where should we look?
Leaving Earth orbit.
Houston, we've had a problem.
Take third exit to Mars. Mars rover collected. Warning. James Webb Telescope. Acquired. Navigate off-road. Voyager probe acquired. Approaching light speed.
Welcome to the 200th anniversary Christmas lectures from right here at the Royal Institution, supported by CGI. My name is Dame Dr. Maggie Adair-Pocock, and I'm a space scientist and a science communicator. Now, all my life, I've wanted to get out there into space. Now, I haven't quite managed it yet, but what I do in the meantime is build instrumentation that help us better understand the universe and answer one of the most fundamental questions of all time. Are we alone? So tonight we're going to continue our journey for the search for life from beyond the Earth, but now out into our solar system. The wonderful thing about our solar system is that it's local. And so what we've been doing over time is actually sending probes out to get up close and personal to these planets. And so it makes our search for life a lot easier because in some cases we can land on these planets. And we've sent one straight towards the sun. Now we've got an animation here of this probe. It's called the Parker Space Probe, and it's got very close to the sun. And so now I'd like to introduce the lead scientist for the mission and head of science at NASA, Dr. Nikki Fox. So, Nikki, thank you so much for joining us. And I know you just flew in. Thank you.
Yes, I did. Yes, and then out again tomorrow.
Tomorrow, so yes, a whistle-stop visit.
Absolutely.
But now, can you tell us more about the Parker Space Probe?
I would love to talk about Parker Solar Probe. I could talk for hours about it. It's a mission really, really close to my heart because it was steeped in sort of history and tradition. It was first proposed in 1958 when a young scientist predicted that the sun's atmosphere, the corona that you see during a total solar eclipse, would be continually accelerated, bathe all of the planets, carve out a protective bubble for us, the whole solar system, as we are orbiting the Milky Way. We are protected by the atmosphere of the sun. Wow. People didn't believe him. And they said, no, it can't be true. The only way we could find it would be to send a probe right into the atmosphere of the sun and actually start to see if he was right and, you know, what was causing it.
The sun, as far as I know, is quite hot, right?
Yeah, yeah, it's pretty hot. Yes.
It's pretty hot.
Yeah.
And so how did Parker do that? How did you protect it against that solar radiation?
Lots and lots and lots of technology. My favourite is the heat shield. And so this is a scale model of the Parker Solar Probe. This is the heat shield here on the front. To give you sort of a sense of scale, this is actually about 2.4 meters in diameter. It weighs about 72.5 kilograms, and it's about 11.5 centimeters thick. It's made of like a carbon, like a graphite epoxy, like you might have in a nice bike or a tennis racket or your golf clubs. That's the type of stuff that it's made of. The important thing for us is it keeps us cool. So if I put on, if we can dim the lights a little bit, thank you. So this is basically like the light from the sun. Now the material that the spacecraft is traveling through is at about 2 million degrees Celsius, which is really hot.
Yeah, I said it was hot.
But fortunately, it's not very dense. And so like if you put your hand in an oven, if you preheated it to 200 degrees Celsius, you don't get burnt unless you touch a surface. Please don't try that when you get home. You can see here, the big thing that we have to worry about is the light from the sun. The front side of this heat shield is at about 1400 degrees Celsius. The rest of the spacecraft, about 30 degrees Celsius. Now, the really big breakthrough for us came when Parker's solar probe was close to the sun, and we were able to see that unlike something that you would put energy into here on Earth, like if you push your bike and then you don't pedal it again, it will slow down. Solar wind doesn't slow down. It goes all the way beyond, way out beyond the orbit of Pluto, way out into the very edge of the solar system.
Yes, and I think we've got some images of sort of some coronal mass ejections. So this huge power surge coming out from the sun. So can you talk us through these?
Absolutely. This is why we care about the sun, by the way, because the sun is not just a bright point of light in the sky. It has these big storms, and this is like a really stretched slinky spring. As with everything, if you stretch it too much, it explodes and all the energy comes out. Now, these big things explode from the sun. They travel about 93 million miles between the sun and the Earth. When they arrive at Earth, they interact with our Earth's magnetosphere, our magnetic protection. During those storms, they actually caused big impacts, and I was lucky enough to be here last year in May of 24, to see a beautiful aurora visible over London. So I hope a lot of you were able to see that.
Because usually they're just much further north.
Much further north. Transoceanic flights were grounded or had to be rerouted because of all of the energy causing radio blackouts. Things like precision navigation, precision landing couldn't be used for many hours. So lots and lots of impacts, all from these really active storms.
Yeah.
So we need to be able to predict them.
Yes, and so it feels as if the sun's out there, so, many sort of kilometres away, but it does bathe our planet with energy. But the question is, where does that energy come from? Well, to answer that question, we've got a demonstration. So let us go back to the very beginning of the universe.
Oh, and here it is.
OK, so now we're going to put on some safety gear. Thank you very much. So let's go back to the time of the Big Bang. Woo. So what we have here is we've just had the Big Bang, and this is what's left behind. Now, most of it is white confetti, but we can see sort of occasional bits of blue.
Yep.
In the early universe, we mainly had hydrogen. That was the only element around, with a sprinkling of the blue helium. So this is our early universe. Now, let us call for 2 volunteers.
Now we want 2 volunteers because we need to sweep this up.
Yes. So
Although
please.
I thought you were all going to put your hands down there. It's fun, trust me.
So perfect, we've got 1 volunteer. We'd like to come and stand in the middle.
Yes.
And we need another volunteer. And so, yes, would you like to come up? So first of all, I'd like to ask, what are your names? What's your name?
Oida.
Oida, thank you. And what's your name?
Alec.
Alec, perfect. So Oida and Alec, what we've done is gone back to the time of the early universe, and you can see the hydrogen, a bit of helium scattered around the universe. But what I want to talk about is how we formed the first stars. So I think we're going to need our first star calendars here. Perfect. So what I need you to do is just pick up some of this hydrogen and helium and put it into our first star.
So they're going to be our gravity.
Yeah, they are.
So could we have the gravity signs?
Oh, perfect.
So now you see,
So
yes,
just put this,
very
thank
important.
you.
You are the gravity of the universe.
Yes,
Right.
gathering up the matter of the universe.
So what happened in the, you can start. Early in the beginning of the universe, so all this sort of hydrogen and helium kind of clumped together, just as they are doing.
So this is all due to the force of gravity?
All due to the force of gravity. Occasionally, the 2 hydrogens will get kind of forced together, lose an electron, and then fuse and form helium.
So yeah, for a star to be a star, fusion needs to occur. So the star needs to get to a critical mass before this can happen, but then the temperatures and pressures are high enough that you get a hydrogen and a hydrogen, they fuse together to make helium, but it's governed by this equation, E equals mc squared. Now, I think many of you would be familiar with this. It was first proposed by Einstein, but this is how stars are so bright. This is where the energy comes from. Because when a hydrogen and a hydrogen come together to make helium, what happens is you lose a tiny amount of mass. And that mass is converted into energy. And so you get the mass, you multiply it by the speed of light, which is 300 million meters per second, the fastest known thing in the universe, but then you multiply it by the speed of light again. So tiny amounts of mass loss converts into huge amounts of energy. Stars are like people. They go through sort of a life cycle.
Absolutely. And we're about to see the end of this life cycle because, as you said, that fusion's going on. And then eventually, the pressure and the temperature caused by the fusion is bigger than the gravity that's holding all of this material together, and it's going to explode.
Actually, it's run out of fuel.
It's run out of fuel.
Yeah. So what we're going to do is we're going to do a countdown, and then this star is going to go supernova. And let's see what happens. So are you ready? From 3. 3, 2, 1. Yes. I should be saying wee, but
Now what can we see? There's a lot more helium.
yes.
And there's some other coloured paper
Actually, yeah,
in here.
I'm seeing these little pink bits.
Little pink ones. So there's still hydrogen, but there's more abundance of helium. And so while this star was undergoing that final sort of bit before it went supernova, the helium were actually interacting and forming things like carbon, oxygen, and neon.
So what we need to do is that has thrown that matter out into the universe again, but now gravity starts doing its work again.
Gravity does its work again.
Start scooping these up,
Yes.
and we'll get them into the next stars.
But now we have carbon and oxygen and neon and maybe a few other things also going in to the beginning of the star to actually, start and kick off that fusion experiment again.
Yes.
And so it just basically repeats, but each time it's getting more and more complex.
Fantastic. I think that's probably enough.
Gravity, I tell you, gravity's working really hard.
Gravity is very efficient. Okay. So now we're just going to go for another sort of stellar evolution. So we're going to actually explode this star. So I think it's your turn. Would you like to step in? And we will watch this star go supernova. Now, supernova are some of the brightest things in the whole of the universe. We can see stars going supernova in other galaxies.
Right.
So let's watch this happen. Okay. 3, 2, 1. Ooh.
Okay.
I just love the colours.
I know, it's great. So now we're making more and more complex elements. So now you're going to have things like sulfur and silicon.
Okay, yes, so gravity, yes. Gravity, we need to do
Gravity,
your work
you've
once
just got
more.
one more gravity.
Yes.
One more.
Yes, and so we're going for the more complex elements.
Right.
And yes, are represented here by the different colours. So thank you, gravity.
Gravity, you're doing a great job.
Yes.
Okay.
Fantastic.
Now you're actually going to let me.
Oh, yes. Now, actually,
Okay.
so if gravity can stand over here with me, as a stellar scientist, I think, Nikki, you need to explode at least one of these stars.
You know, I've always wanted to do this. Okay.
Right.
Ready?
So I think we're ready. 3, 2, 1. Whoa. So now we've got the hydrogen, we've got some of those higher elements, but we're getting some metallic elements as well.
And that's really important because
Yes.
as we look in our solar system, we look at all the different bodies that we have in our solar system. We've actually found 8 metallic asteroids. And so we know that when our planets and our sun was really forming, that these elements were all around in the environment as the sun formed, as the planets were generated. This is the stuff that you're made of. So you have calcium in your bones, you have oxygen that you breathe, you have nitrogen. Everything in your body comes from this early universe. So you guys are all made of stardust.
Yes. So we truly are part of this amazing cosmos.
Absolutely.
So I think a big round of applause to our volunteers here, please. Can you put the logos on? I want to say thank you, Nikki. And I think you'll be joining us again later.
I will, yes. I can't wait to hear the rest of it, though.
Thank you so much.
Thank you so much.
I'll see you later. Okay, so that's talking about stellar evolution. So our local star plays a vital role in life here on Earth. But has that radiation fueled life on other planets? So to find out, I think we need to visit those other planets, the planets of our solar system. Now, as we visit each planet, I'm going to give you a few facts and figures, but I want you to vote as to whether you think there might be life on each planet we visit. So yeah, yes for life, no if there's no life, or maybe somewhere in between. Now, when we go through this, we're going to note your scores and we're going to put them on the planetary scoreboard. So I've got my astro assistant, which happens to be my daughter, to help me do the scoreboard. So Laurie, if you'd like to come up. And a round of applause for my daughter, please. So let's get this journey started. So what is the first planet out from the sun? Mercury. And there it is, Mercury, planet closest to the sun. Now, I think you know the drill. What I'm going to do is going to use warp drive to get there. So are you ready? I'm going to do a countdown. 3, 2, 1, let's go. I like your noise. Okay. Now, a few facts about Mercury. Mercury is diddy. It really is a tiny planet. And I said it looks like a moon. It's only sort of 1.4 times the size of the moon. A temperature on Mercury is about 167 degrees C. So it has a very hot side when it's pointing towards the sun and a very cold side. So it's a planet of extremes. Now, does Mercury have water or liquid water flowing over the surface? We don't think so, because on the day side it will just burn off and on the night side it would freeze. But we do believe that Mercury probably has pockets of water, but frozen water in sort of nooks and crevices which don't ever see sunlight. Now, just one interesting fact about Mercury. If you go from sunrise to sunrise, that is 176 days. But a year on Mercury is only 88 days. So a day on Mercury is actually longer than a year on Mercury. So that's a few facts and figures to base your decision. So now, Laurie, if you can come and help me, what I want to ask you is there life on Mercury? And remember, yes, no, or maybe.
Okay, I'm seeing like just no.
Actually, one or two
Yeah,
maybes.
maybe a
I see a
couple
bit of a
maybes, but
wobble there.
I'm seeing just no.
Okay, so I think it's a majority of no. So we are concluding that there's probably not life on Mercury. Thank you very much, Laurie. Let's put that up there. So where are we going next? What is the next planet out from the sun? Venus. Okay, perfect. Let's put it up there, Laurie, on the scoreboard. Thank you. And there's the planet Venus. So let's use warp drive to get there. Let's go. The planet Venus. Now, you don't usually see the planet Venus like this because Venus actually has a very thick atmosphere. And one of the things that you might not realise is actually the planet Venus you've probably seen yourselves, but you might not have noticed it. If you're up soon after sunset or right up early soon after sunrise, sometimes you see what looks like a really beautiful star in the sky. But it's not a star, it's actually the planet Venus. So in 1970, Russia sent the Venera 7 probe to Venus. And it was the first probe to have a soft landing on another planet. We've got a demonstration here to show what happened to Venera 7 when it landed on Venus. So thank you very much. So here is our space probe, Venera 7. Now, in this case, our space probe is actually made out of the metal gallium. Yes, now gallium has a very low melting point, and this is what happened to the Venera space probe as it landed on Venus. I've got a hush there. Yes. Because we thought that the planet Venus might be sort of lovely and habitable. It looks so beautiful in the night sky. But when the probe actually landed on the surface of Venus, it could only transmit for about 23 minutes. Because after that, this is what happened. The probe started to melt. Now, so why did it melt? Well, it turns out that the planet Venus, although it's very similar to Earth, so it's about sort of just under the size of Earth, the planet Venus is incredibly inhospitable. The average temperature on Venus is 475 degrees C, which is why it melted the probe. Venus is actually hotter than Mercury, even though Mercury is closer to the sun. So why is that? Well, it's because on the surface of Venus, it has many volcanoes, which are spewing out greenhouse gases. And so that means radiation from the sun gets trapped in the atmosphere of Venus, and Venus's temperature is elevated. So, oh dear, it's not looking very good, is it? Now, I think when the Venera 7 probe landed on Venus, it didn't quite melt as much as this, but it did melt, and that's why it could only transmit for a little while. But what we have found is that if you look actually in the atmosphere of Venus, about 60 or 50 or 60 kilometres up, there the temperature is a nice mild 25. So it's like a sort of the UK on a summer's day. And so if there could be life that actually sits in the atmosphere of Venus, but we don't think that life as we know it could survive on the surface. But there's one other thing. There was a recent detection in 2020 of a molecule called phosphine. Now, phosphine, we believe, is a possible indicator of biological life. And so the fact that we think we've detected phosphine in the atmosphere could be an indication of life on Venus. But with all these things, we've got one detection, and so we need to verify it with others. And so other people are looking into it now. So that is the planet Venus. And what I need you to do is, Laurie, you're on scoreboard duty, is whether you think there's life on Venus.
Okay. Quite a few maybes.
Actually, I'm seeing mainly maybes. Okay, so perfect. It's a maybe for Venus. So where are we going to next? What is the next planet out from the sun? Earth. And so, yes, let's put it up on the screen. There's Earth. We've got it on the scoreboard. And so let's use warp drive to get to Earth. The pale blue dot, our glorious planet. Now, we know a lot about Earth, so I won't dwell here. But, you know, we know its size, average temperature on Earth about 15 degrees. It has a thick atmosphere, and it's made out of nitrogen and oxygen. And it has that magnetic field that we were talking about earlier, that magnetic field that protects it from things like the solar wind. And in terms of water, we know it has lots of surface water. In fact, I think 4/5 of the Earth's surface is covered in water. So it's a slightly rhetorical question, but do we think there's life on Earth? So, Kate, Laurie, what are we thinking?
This isn't hard.
This isn't hard. It's Earth, I know. But I'm looking for the maybes. See, I knew there would be one. There's one person pointing down.
I think it's a resounding yes.
I think it's pretty much a yes. So let's put a yes for Earth. Thank you. And so where are we going next? What's the next planet out from the sun? Mars. OK, Mars. And so, yes, let's put it on the solar system map. It's there. It's on the scoreboard. Let's warp drive to Mars. The red planet. Now, it's quite interesting because I think Mars is some of our biggest hope for finding life out there. And we've sent many, many probes to the Martian surface. We are celebrating the 200th anniversary Christmas lecture. So I would first like to say that I'm extremely honoured to be the 200th Christmas lecturer. Because when I was a child, I used to watch the Christmas lectures at home, and one of the ones that really stands out in my mind is watching, in 1977, the Carl Sagan Christmas lecture. Now, he introduced the audience to the latest findings from the Viking probe. And he invited 2 volunteers to come and join him on the stage in a mock-up of Mars. And this is a clip of their conversation speaking about the future of rovers on Mars.
You see, here we are stuck in one particular place on Mars, and it would be nice to go to other places. To do that, we would have to have a spacecraft which could move about on Mars, which could rove. Would you like some milk in there, or would you take it black? Some milk, yes. And so we have to have a spacecraft with wheels, with tractor treads, which could land in the safe and dull places, like here. It's not so dull because, after all, we're having tea, but it is dull compared to almost everywhere else on Mars. Would you like some milk?
So, fast forward 50 years, and we've sent 6 rovers to Mars so far. And many of them are similar to my friend Bruno here. Now, I would like to introduce Charlie Rowe, who is a space engineer and in charge of Bruno. Charlie, what is Bruno?
So Bruno is a very early development model of the Rosalind Franklin ExoMars rover. That is Europe's first rover and first rover to Mars, and it's going there to find signs of life.
Rovers already on Mars have been coming back with data. So what have we found out so far?
Lots of missions have been to Mars in orbit, and rovers as well. NASA and others have sent rovers very successfully to the surface of Mars. The most recent kind of missions have gone and found evidence for flowing water and the conditions we would want to find if there was past life. Rovers like Curiosity and Perseverance have found evidence of riverbeds, so you can see here the kind of lines where river channels may have run. So I mentioned Curiosity and Perseverance. Curiosity landed in 2012, Perseverance in 2020. They sent back pictures of rounded pebbles like this, which we would typically on Earth find at the bottom of riverbeds where there's flowing water and erosion.
So just to be clear, this is actually a picture from the Martian surface.
This is a picture from the Martian surface.
And it's showing water erosion.
It's showing water erosion, we think, on these pebbles that's rounded them, which is strange because rocks on Mars are typically very sharp, and that's because of the lack of erosion on the surface. So this is why these really stand out.
OK, so that in certain areas we see rocks like this.
Absolutely.
And I guess that's a strong indication that Mars once had water.
Once had water, yeah, absolutely.
Lovely.
And then more recently, the Perseverance mission, NASA's latest rover, still working on the surface, found strange textures in rocks. You can see the leopard print on the rock here.
So that's these dark bands?
That's these dark bands that you can see there, exactly.
And so what did that tell us? Or what did it give us an indication of?
We think it's an indication of a biosignature. So this is something that on Earth we might find in the presence where organic molecules or elements have interacted with the surface. So that's one way these can be formed. More data would be required, but it's certainly intriguing.
Lovely. And I guess it's a sort of an area we're going to go back and revisit. And yes,
Absolutely.
and do more research.
Absolutely. And
Thank
here we are.
you. Yes. So thank you. I think we're going to go on to something else. But if you could stay here, because we'll be coming back to Bruno shortly.
OK.
Fantastic. Thank you. So we were seeing there that there's lots of evidence that suggests we used to have water flowing over the surface of Mars. But the question is, what happened to that water? Why did the atmosphere change? Well, to find that out, what we're going to do is a demonstration. Bring on the hot cannonballs!
Hello.
Hello. You've got the hot cannonballs?
I have got hot cannonballs. Yeah. They need to be in the oven a little bit longer.
Yeah, but I'm really hoping they're hot. I mean,
they're hot. They're hot.
I'm going to stay over here.
Good idea.
So in the early solar system, and when the planets soon formed, they were sort of hot. But now, as the solar system has got older, that sort of lava stage of the early planets, they've began to cool down. So what we have in this furnace is two cannonballs, one representing the size of Earth and one representing the size of Mars.
That's right.
Perfect.
I've got a ball that's about twice the size of the other, one for Earth, one for Mars. They're in there, so they should be the same temperature,
Yes.
about 800 to maybe 1,000 degrees Celsius.
I'm taking another step back. Yes. So Dan is going to actually bring the hot cannonballs out and put them on those stands. And what I want us to do is see how the two cannonballs cool down. Is there a difference in the cooling? Let's get that started. Thank you.
I'll go for it.
So now, if you see one cannonball that looks cooler than the other, I want you to shout out the name of that cannonball. So if you think the Earth ball is cooling quicker, shout out Earth. If you think the Mars ball is cooling quicker, then just shout out Mars. I'm going to stand over here and look myself. I'm going to take that as a Mars. OK. Thank you so much.
My pleasure.
So, we are seeing Mars, actually, and as we bring the lights up, I think we can see the difference quite clearly here. So Mars seems to be cooling down quicker than Earth. And this is what we believe happened in the solar system. So they probably started off fairly reasonable, equal temperature, but Mars did seem to cool down quicker. Now, one of the important factors that we have on Earth is that Earth has a semi-molten iron core. Now, this iron core, as the Earth rotates, that semi-molten iron core moves, and that generates a current, and that generates a magnetic field. Now, that magnetic field protects us from things like the solar wind. That's what Nikki was talking about earlier. Now, we think that Mars used to have a similar semi-molten core, but because Mars is smaller, it cooled down quicker, so its molten core solidified, and it lost its magnetic field. And then particles from the solar wind just eroded the atmosphere away. So we think about a few billion years ago, there was liquid water running over the surface of Mars, but the loss of its magnetic field enabled the erosion of its atmosphere. So thank you very much, Dan. The hot cannonballs. Perfect. So Charlie, would you like to join me again? So, Charlie, you mentioned this is the prototype for the Rosalind Franklin rover. There have been many rovers on Mars, and we haven't found much definitive evidence. Why would Rosalind Franklin be different?
The main thing about this rover, I don't know if you can all see it, but is the black box on the front here. And inside this box is a drill that folds out, and it allows it to drill down to 2 meters. Now, we think that about half a metre of soil and rock is enough to protect the lower layers from the really harsh environment on Mars. So you can see in this video that there's a drilling demo of what the real rover does. So Maggie, that environment you described on the surface of Mars, losing its magnetic field and it's lost lots of its atmosphere, has meant the surface is very, very harsh. So we think those upper layers are just enough to protect the lower layers and preserve what evidence is down there. So this drill, it drills down to 2 meters. It uses a combination of equipment on board to pick the perfect site. At 2 meters, it can take a sample, bring it up, pass it on board to the inside of the rover. So most of the instruments on the rover sit inside the main body. We call it the bathtub because of how it looks. And inside there are a suite of instruments that allow us to analyse those samples and search for signs of life.
Perfect. Well, thank you very much, Charlie. And I think a big round of applause for Charlie and for Bruno. So that is our current understanding of Mars? Louis, we need you on the scoreboards, and let's vote if you believe there's life on Mars today. Vote now. Ooh, OK.
That's less yes than I was expecting, actually.
Yeah, I'm seeing quite a few maybes.
Yeah,
I think maybe.
maybe, yeah.
OK, perfect. But we're not going to stop it there, because we also need to vote for life, the possibility of life on Mars past. So, again, vote now for life on Mars past.
OK.
Ooh.
That's...
OK, actually, it's pretty resounding,
Yeah.
isn't it? Yes, OK, so I think we think that there used to be life on Mars. Perfect. Go ahead, my love. Thank you. So, which planet are we going to next? Jupiter. Yes. OK, let's use the warp drive. I must say, your noises are getting better and better. So yes, the planet Jupiter, the largest planet in our solar system. Now, there has been a probe that has been going around Jupiter, and it's called Juno, and it's been sending back these amazing images. So this is real data from the planet Jupiter. And what we're doing is we're seeing its outer atmosphere. And you can see there's all sorts of swirls and eddies in the atmosphere, so it's amazingly complex. Also, Jupiter has a strong magnetic field. Now, a few facts and figures about Jupiter. I mentioned it's the largest planet in our solar system, so it's actually 11 times the size of Earth. Average temperature on Jupiter, about minus 110 degrees, so definitely nippy. Like many of the planets of the outer solar system, it's about 90% hydrogen and about 10% helium. Now, surface water. There's a challenge with this, because with these gas giants and these icy giants, we don't actually know if they have a surface. We can see the outer atmosphere, but we don't really know what lies below. Now, we're talking about sort of sending a probes to Jupiter, and we saw the wonderful images we're getting back from Juno. But what if we wanted to go deeper? What if we wanted to know what lies below the atmosphere? Well, to talk about that, we have another demonstration, and of course, I'm going to need a volunteer. Ooh, lots of hands. Actually, yes, I think, yes, would you like to come up? So first of all, can I ask your name?
Tiwa.
Tiwa. Very nice to meet you. Now, this is our Jupiter. If you'd like to come in here. So this is the layers of Jupiter. So up here, we've got the upper atmosphere of Jupiter. That's what we can see from space. But down below, we have various layers. And the problem is, at the moment, we don't know what those layers contain. We don't actually know what is at the heart of Jupiter. Some people say it might be a slushy metallic core, and that's represented by this shiny stuff here. But the truth is, we don't know. So maybe in a distant future, we might send probes to Jupiter, and we might send a number of different types of probes to Jupiter, going to the different depths of the planets. So let's start with a first one. Let's say we want to go deep. This is going to represent our first probe. So if you'd like to hold that, see, it's quite heavy, isn't it? Quite dense. Now, will you hold it right at the front when you drop it, and we'll see how deep it goes. So let's drop it. 3, 2, 1, drop. Ooh, that came crashing. And you see, we get sort of interference between the layers. And I think that dived down quite deep. And I can see it just here. I think that's where it's got down to. So it's gone down to the inner layers of Jupiter. OK, so that's quite a dense probe going deep into the atmosphere. OK, so let's try another probe. What if we want to look at some of the outer atmosphere and sort of going into the first layers? So I think for that, we'll try a ball like this. Now, what do you think the density is now? It's very light. So we've got quite a large volume, but very light, so low density. So again, if you could hold it at the front and then drop it in, we'll see where that ends up. OK, so we've gone through the atmosphere, but we're just landing where it gets a bit more dense, which makes sense. But finally, in the future, we may want to send humans to Jupiter. Now, this will be quite a mission. But yeah, so what we need is something that represents the density of the human body. And what we have here is a large grape. How deep do you think this is going to go into Jupiter's atmosphere? Now, just call out some names. So we've got sort of yellow, we've got red, or will it go into the metallic core? OK, well, there's only one way to find out. Remember, hold it at the front, and let's drop it in. Plop. Ooh, ooh. Blue. Actually, yeah, blue on the cusp of the metallic core. Now, I must point out that we probably wouldn't do this, because as you go deeper and deeper and deeper towards the core of Jupiter, the pressure gets higher and higher. I think we're a long way from the sort of technology you'd need to protect a human body from the crushing pressures that you'd experience in Jupiter. But a big round of applause for our volunteers, please. Thank you very much. So that was our brief visit to Jupiter, but let's get on with the scoreboards. So please vote now. Life on Jupiter, yes, no, or maybe?
Okay, I'm just seeing no.
Ooh, okay, I'm just seeing no. An occasional maybe, but yeah, I think it's...
I wouldn't want to live there, I don't blame them.
yeah, I wouldn't want to go there. Yeah, you saw what happened to that grape? Okay, so probably no life on Jupiter. So let us continue our journey. What is the next planet out? Saturn. Yes, of course, Saturn. It's up there on the map. It's there on our scoreboard. Thank you, Laurie. And so let's use warp drive. Let's go. Ah, Saturn and its beautiful rings. The most of what we know about Saturn is due to a probe called Cassini. And Cassini sent back some stunning images. Now, Cassini was one of those spacecraft that went to Saturn, and it stayed out there for 8 years in orbit about Saturn. And it told us about the planet itself, it told us about many of the moons of Saturn, and it told us about the rings of Saturn. Now, just to give you a few facts about Saturn, Saturn is about 10 times the size of Earth, average temperature about -40 degrees C, atmosphere very much like Jupiter, it's mainly hydrogen and helium. Again, surface water, we really can't tell. Below that outer atmosphere, it's hard to see what's going on below. But I think one of the interesting facts about Saturn is its rings. Because the rings are sort of very narrow. They're only a few hundred meters deep, but they surround the whole of the planet. And also, the rings are actually made up of lumps of rock and ice about the size of my fist. But they reflect the sunlight, and that's why we see them so clearly. Some people think that the rings might have been made up of a moon that got destroyed back in the past. So, Laurie, you're on the scoreboard duty, and let's vote now. Do we think there's life on Saturn?
I think it's mainly no.
I think it's mainly no. OK, Laurie, thank you very much. If you'd like to apply that. So we've been talking about these gas giants of Jupiter and Saturn, and it looks as if the probability of finding life there doesn't seem very high. But it's quite interesting because one of the things we want to do is explore the moons of Jupiter and Saturn's system, because between them they've got about over 350 moons going around them. Now, to talk about this, I'd like to introduce Associate Professor of Space Instrumentation at Oxford, Dr. Carly Howard. So, Carly, tell us more about what you do.
So I work to explore the outer solar system. So anything inside of Jupiter is interesting.
Just not interested.
No, we've been there.
Moving on.
So Jupiter and outside. Yeah.
OK, perfect. And so we're going to talk about some of the moons of Jupiter and Saturn.
Brilliant.
So what's first up?
First of all, we're going to look at Europa, which is one of the moons. This is Europa, one of the moons of Jupiter. So Jupiter has lots of moons, over 90 moons. But there are 4 that are the big ones, OK? And Europa is one of them. So we also have Io, which is a bit more rocky, Ganymede and Callisto. But we're going to focus on Europa because I think Europa is a great place to look for life.
OK. Now, this seems like an unusual, because, I mean, we talk about planets in the habitable zone.
Yep.
But talking about moons now, it seems like a new deviation.
It is. We weren't really sure where life could exist. As you've said, we've had ideas across the years about where they could exist. But Europa is a great one because there's this new idea about following the water, and Europa has water.
OK. And so where do we have evidence for this water?
Well, first of all, the surface is water. Right? What you're looking at here, it looks like it could be rock, but actually it's liquid water, and it's just incredible. Its surface is icy down to about 30 kilometers, and then there's 100 kilometers of liquid water ocean underneath it.
And what I love is that we're looking for life on some of these moons because of something we discovered right here on Earth. And the deepest part of the ocean on Earth is the Mariana Trench, and that sits 11 kilometers below sea level. Now, when we got there, we were aware that, light from the sun doesn't penetrate down here. And so we didn't think there could be any sort of ecosystem that could survive down there. But when we got down there, we realized that there were these thermal vents, heat energy that we were talking about, escaping from the center of the Earth, and it's powering these thermal vents. And where they thought there could be no signs of life, this is what we saw. Can you tell us a bit about this life?
So there's no sunlight, right? Well, you're seeing images here because we took lights with us. So where we get sunlight on the surface, the energy here is coming from the core of the Earth through these little vents, and that's what's powering that life. That's that energy source.
So I think we also got some information from a spacecraft called Galileo.
Yeah, so Galileo went around and it took these amazing images of Europa and it gave us that first idea of what could be going on. And we know that Europa is sitting so close to Jupiter. Jupiter's enormous. It's got a massive gravitational field. And that's the source of energy on Europa.
These moons are quite small. So if they had heat, they've probably lost that heat a long time ago. So where's this heat coming from?
So you're right. It's not the heat from formation. This is energy that Europa and its other moons are getting as it orbits Jupiter. So sometimes it's closer, sometimes it's further away, and that squeezes and relaxes the core of Europa. And energy can't be destroyed. That energy that comes from the squeezing and relaxing has to be dissipated, what we call it. So it's going to be emitted as heat. And it's maybe a little bit easier to visualize on a squash ball. Anyone that plays squash or racquetball, you might be familiar. You have to squeeze and release that ball in order to warm it up before you play. And that's what's going on in the core. This squeezing and releasing is happening, but to the middle of these moons. And that's getting then lost as heat.
And so what's your favourite moon of Saturn? Go and tell me.
Oh, I mean, everyone has a favourite moon of Saturn, and of course it's Enceladus, right? Enceladus is just brilliant. So it's a little bit, this is Enceladus, a little bit like Europa in the sense that it has an icy shell and it has liquid water underneath. So you're kind of getting the theme, right? We're into water. But unlike Europa, there's an idea that Europa might have plumes, but Enceladus definitely has plumes, and Cassini, the spacecraft, went there and explored it, and we saw images like this. What a phenomenal image.
Actually, to me, this is beautiful.
It's stunning, right? So you can see the day side, the night side, and then these plumes that are coming up from the surface. And you can see that where this plume material gets above the terminator, it hits the sunlight, and then we can see it again. So these plumes are actually coming from fractures on the surface that you can't see in this picture.
Yes.
But these are the fractures. There are 4 fractures at the South Pole, and we call them sometimes the tiger stripes. And we know by flying through the plumes that the plume material is actually ocean material. We see things like rock, and we see the antifreeze of that ocean in the plume material. And so we know when we fly through the plumes, we're sampling that subsurface ocean.
So before you leave, I just want to ask one more question.
Yep.
Do you think there's life within our solar system?
I do, and I think if there is life, it's on Enceladus.
It is your favourite, though.
It is. I'm heavily biased. I acknowledge that. But yeah.
Well, thank you. A wonderful round of applause for
Thank you
Carly.
so much. Thank you, everyone.
Now, Carly mentioned Enceladus, one of the moons of Saturn. But one of my favourite moons of Saturn is actually a moon called Titan. Now, Titan, we have actually visited, and Titan was part of a mission for the Cassini-Huygens space probe. So I mentioned Cassini earlier as one of the missions that went in orbit around Saturn. But as well as Cassini, there was Huygens. Now, Huygens was designed to land on the moon Titan, and this is what it saw. But not only is it what it saw, it's what it heard. Because what it turns out is that Titan has an atmosphere rich in methane. And so you can hear that rumble. That's actually as the probe fell through that methane atmosphere. And what we saw as we actually landed onto this moon was sort of mountains, river tributaries, all sorts of amazing features on a moon. And so we saw these river tributaries and we were thinking, so this is a long way away from the sun. Out here, it's pretty cold. So what is causing these rivers? And it turned out that it's liquid methane. Way out here, the temperature is cold enough that methane is a liquid. And so now, what I want you to do is have another demo to introduce you to liquid methane. Oh, I love it when they come on bubbling. Fantastic. So, Dan, what have we got here?
So I've brought you a balloon of methane gas.
Oh, I see. OK.
Yep.
So now methane gas is the sort of thing we have in our gas cookers. But what we're going to do is we're going to liquefy it. So how are you going to do that?
So in here, I have some liquid nitrogen, which is extremely cold, about minus 196 degrees Celsius.
Yes. And do we know at what temperature methane liquefies?
It's around, if I've remembered rightly, about minus 188. So a little warmer than that is cold.
OK, lovely. And so if you put the methane gas into the liquid nitrogen, it should turn into a liquid. So let's give it a go. Now, as it sort of condenses down, we're going from gas to the liquid, so the balloon's getting smaller and smaller and smaller, and in a second, what we'll do is take it out and see that liquid methane.
If it makes it all of the methane into a liquid, there won't be any gas, and the balloon should suck itself inside. Yeah, I've got to Try and get it out before it breaks. Got it.
Okay, perfect, lovely. So we've got the liquid methane, but we need a means of getting rid of it. So what we're going to do is pour that liquid methane into this tray and set it on fire so we can just get rid of it safely. So I think here we go. Liquid methane.
Just got to warm up a little bit, get it back to gas. There we go.
So yes, so a blue flame, just like we have in our gas cookers at home. Woo!
Thank you very much.
Thank you very much. So do we believe there might be life on the moons of Jupiter and Saturn, especially Europa, Enceladus and Titan? Let's have a vote. Yes, no, or maybe. So what were you thinking?
I was thinking a lot of yeses and a lot of maybes.
So shall we say a tentative yes?
We could do both.
I like your style. OK, so we're going to do yes or maybe because we don't know. But the thing is, before we've discovered that life in the Mariana Trench, we wouldn't have even been considering this. So it's just another possibility of finding life in our solar system. Thanks very much, my love. And so, yes, let us continue our journey to the outer parts of the solar system. Next stop is Uranus. Are you ready? Let's use the warp drive. OK, warp drive has taken us to Uranus and Neptune. Now, it's quite interesting here because we're seeing this is the planet Uranus, and you can see two things about it which are slightly odd. Firstly, that it has a ring. Now, it's quite interesting because when we think of ringed planets, we think of Saturn. But all the planets of the outer solar system, so Jupiter, Saturn, Uranus and Neptune, all have rings. Now, this is an interesting fact about Uranus. When you look at the spin of Uranus, it's actually spinning on its side. The atmosphere of both Neptune and Uranus is mainly methane, and that's what gives it the blue colour. But so let's talk a little bit about Neptune as well. One of the things that is quite interesting is how these planets were detected. These planets, unless you really know what you're looking for, you can't really see them with the naked eye. And so we know of the planets of sort of the inner solar system. The ancients knew about Jupiter and Saturn, but the planets Neptune and Uranus, people didn't know very much about. So, how did they detect them? Well, I've got another demonstration to show you how this works. And for this, I need a volunteer. Oh, gosh. Yes, blue top in the middle with the hoodie. Yes, do you want to come on down? Thank you. So, first of all, what's your name? Ela. Ela. Very nice to meet you. Now, what we're going to do is imagine this is our backdrop of stars. So this is the outer parts of the solar system. Now, what I want you to do is I'm going to give you a piece of chalk, and what I'd like you to draw is, if I'm going to come over here and put this ball on the ramp, and it's going to roll down, draw me the path you think the ball is going to take. So from there, it's going to follow, I think, pretty much a straight line and go all the way to the bottom. OK, so that's perfect. So now I'd like to give you the ball, and if you stand here, right at the end, I'd like you to, when I say, actually, we'll say 3, 2, 1, and then you release the ball, and let's see what happens. So are you ready? 3, 2, 1, release the ball. Whoa. OK. Well, now, we're scientists, so I think we should just do that one more time. Maybe there was a sort of something on the surface or, something to disturb it. So let's just do that one more time. 3, 2, 1. Whoa. So there's quite a deviation there. So thank you very much. I think a round of applause for our volunteer. Thank you very much. Thank you. And what we need to do now is analyse what just happened. So, I mentioned that Neptune and Uranus are very hard to spot with the naked eye from Earth. And Uranus was detected using sort of large telescopes, scanning the skies, and they realised there was something out there. But Neptune, no one really had any idea that it was out there until they started doing experiments like this. Because what they were doing is they were looking at the orbit of Uranus, and they realised that the orbit of Uranus sort of had a bit of a kink, a deviation. And so what they realised is that thing that was causing a deviation, a gravitational pull, was probably another planet. So thank you very much, and I think it's time again, Laurie, to do the scoreboard. Thank you.
Probably got Uranus up there.
Yes.
There we go.
Now what I want you to do is vote on whether life is out there. Ooh, that's
okay.
resounding.
That's a no.
Yeah, actually, yeah, I don't think I can see any maybes. Okay, so let's put that on the scoreboard, my love. Okay, so now we've travelled through our solar system. There we have the playground, and this is where we've been searching for life. And I think out there, we also, of course, have the planet Pluto. Yes. Now, Pluto, we're not going to stop there because it isn't actually officially a planet. Yeah, when I was a child, Pluto was a planet, but of course now it's not. So we won't dwell on Pluto. But now it's quite interesting looking at our scoreboard. These are the sort of places we've been looking for life, and we've got one or two indicators. I think Earth is a bit of a cheat. We're pretty convinced there's life there. We think maybe on Mars and possibly on some of the moons of Jupiter and Saturn. Now, the Voyager spacecrafts were launched in 1977, and there were two spacecrafts, Voyager 1 and Voyager 2, and they travelled out into the solar system. And so what I'd like to do is invite the head of science at NASA back to the stage, Dr. Nikki Fox. So, Nikki, can you tell us a bit more about the Voyager missions?
Oh, I'd love to. So obviously there's two of them. They were launched nearly 50 years ago, launched in 1977 separately. They were designed for a 5-year mission to fly past those 4 outer planets that you've just been talking about. They sent back all that spectacular data, and then they continued onwards.
Oh.
And so, you know, after passing sort of the passing Neptune and that orbit, they then became what we think of as like an interplanetary mission, and now they're an interstellar mission. And just to give you an idea of the distance, it takes light 8 minutes to travel from the sun to the Earth.
Yes.
About this time next year, the Voyager 1 will be 1 light day away from Earth. So that means when we send a signal, we want to send a command, we'll send it. It will take a full day for the light to travel out, and it sends a message back to us, and that's another day for that to come back. So
and that's
just a
travelling
year.
at the speed of light,
At the
300
speed of
million
light.
metres per second, and it still takes a day to get there.
It will take a day to get there. Voyagers are just wonderful.
I know. And the things they have transformed our understanding and given us a better understanding of the scale of our solar system.
Absolutely. Also, the fact that that boundary between where the sun stops and interstellar space starts, it isn't just like a point, it moves. So the space weather we talked about at the beginning, the sun, it actually causes kind of the heliosphere to sort of move and breathe as well. And we had to watch the data and really sort of predict what the boundary would look like. Every day we would get data sent back from Voyager 2. The actual tape recorder on Voyager 2 doesn't work anymore, so we only get it when we're listening to it.
The fact it's the tape recorder, I think, really dates it.
It does. It does. But we were, you know, just sitting together, watching the data come in every day and waiting for that to go to 0. And when that went to 0, the cosmic ray population, which is what's outside the solar system, shot up, and we could actually put our finger and say that's the
mark.
moment.
But I think they took that data and converted it into sound.
They did.
And I think we actually have the sound.
Wonderful, from the plasma wave instrument.
Yes.
Yep, this is from Voyager 1.
So yeah, the plasma wave, and we're hearing the sound.
Yep. And that's the actual sounds coming from the very edge of the heliosphere. Yeah. How cool is that?
So yeah, that is the sound of the edge of the solar system. In translation.
Yeah.
Yes. I have to ask a question. Do you think there's life within our solar system?
I do. One of our core objectives is searching for life elsewhere in the universe. You know, you've already heard the wonderful stuff about Enceladus and about Europa. We're sending missions to Europa. We're also sending Dragonfly. You said Titan was your favourite. So we are sending Dragonfly, which is like a large drone that will sort of land and then fly over Titan, looking for like the ingredients of life. For me, it's getting used to maybe not life as we know it, but life as we don't know it.
How about life out there? Because that's where we're heading. We're in interstellar space now, heading out beyond. Will we find life out there?
It will take us a long time to actually do in situ measurements there, but we have spectacular astrophysics telescopes. So yes, watch this space. Watch this space, literally.
Perfect, yes. So thank you, and a big round of applause for Dr. Nikki Fox. Thank you. So, we were just speaking with Nikki there about how we can convert a Voyager data into noise, into sound. But I want to speak to you now about someone who's taking that a step further, because he's taken Voyager data and converted it into music. So I'd like to introduce scientist and composer Domenico Vicinanza.
Lovely to see you. Thank you.
So yes, we were looking there at how we've converted Voyager data into just a sound, but you've converted it into music.
Yes, so the piece I've written is a celebration of the 40th anniversary of the launch of Voyager 1.
Okay, lovely.
And so what I did was using an instrument that is on board of Voyager 1 that is able to count the amount of tiny charged particles that are around Voyager 1. Yes. And what I've done is converting that measurement into melody. So 23 C, 24 C sharp, 25
okay,
D.
yes.
So the larger the number, the higher the pitch.
Right.
Lower the number, lower the pitch. We can think about this measurement as the amount of special cosmic dust around Voyager.
Okay, perfect.
So when Voyager is traveling from, let's say, Jupiter to Saturn, pretty empty, not much dust, low number, low note,
Yes.
really low. When Voyager is approaching a planet like Jupiter or Saturn, the melody rises because the
Get
amount
more
of dust,
particles.
exactly.
Lovely.
And finally, when Voyager leaves the solar system, we are going to hear at the very end that at a certain point the music goes really high and stays high. And that's because in the interstellar space, there's a lot of very special dust, galactic dust.
Ooh.
So by listening to this, we can actually have an idea about the story of
perfect.
Voyager going through the solar system, shooting into the interstellar space.
Yes, we're going to listen to the piece of music now, but at the same time, we're going to see the puppeteers of Ours Circus Theatre performing to that piece of music. So let's take a seat over here. We've made it to the edge of our solar system, and what a fitting way to end. And we haven't found any life here, but now we're going to start a new journey into interstellar space. And this is our new playground, our galaxy, the Milky Way. Think you've got what it takes to run a space mission? Step into command with the Open University's interactive experience and meet the experts that make it happen. Scan the QR code on the screen or visit connect.open.ac.uk/RI2025.